Hi everyone. Let's solve LeetCode 1345, which is a jump game 4. The question says given an array of integers ARR, you are initially positioned at the first index of the array. In one step, you can jump from index I to index I plus 1, where I plus 1 is less than ARR dot length, I minus 1, where I minus 1 is greater than or equals 0, and j, where ARR of I equals ARR of j and I is not equal to j. So, which means you can jump only to indices where either forward or backward, provided they are within the bounds of the array, and to any other index where the value is same but not the same index, right? And you are supposed to return the minimum number of steps to reach the last index of the array. Notice that you cannot jump outside of the array at any time. Cool. So this is a variation of jump game 3, I would say, which I had solved yesterday itself. So coming to an intuition that this is a graph problem is like very uh, easy for me. But the thing is, how do you implement the graph without doing it in O of n square? The first two cases are like pretty straightforward, right? You can just do I plus 1 and I minus 1 and then construct the graph. But how do you construct the graph for this? Also, is it necessary to place all these indices in the graph is the question. Can we do it dynamically, like without placing the indices? I am just thinking, let me just dump down my thoughts here. I will have a graph, and the graph would be like I to I plus 1 and I minus 1, right? So this would be my graph. Should I also put the j index over here? In case I put, how will I be putting? I will have to have another dictionary where you have the value, and for each value at which indices the value has been repeated, that would be present as the value of the dictionary in list. So I'm just thinking if to construct the graph that way, then I'll have to traverse every key of the dictionary, and then for every I, I'll have to create edges from I plus 1 to every other. Okay, got it. So that is like again around of n square, right? This is what I was thinking. If I have indices, let's say I store it as 100. For example, for example, one test case, 100 has come at 0 and 1, 2, 4, right? Yeah, so it has come at 0 and 4, right? Now, to add these indices as well in the graph, I'll have to traverse through every single element and then create edges. Let's say there was some other here as well. Then I'll have to create 0 with 4, 0 with this, 0 with this, and then again 4 with this, 4 with this, which is again like O of n square, right? Can I, uh, so one approach is store them as they are, right? And then while performing the BFS or the Dijkstra, okay, I think Dijkstra is not required over here because the graph is like not weighted. Right? So it would be a simple BFS. So while doing the BFS itself, first you traverse through the graph, and other thing would be traverse through this, right? Yeah, this can be a good idea of going about. Let me try and implement this. N would be my n of array. I create the graph. Okay, now I'll have to traverse through the array and then construct the graph. less than n, graph of I dot append I plus 1 if I minus 1 is greater than or equals 0, checking for bounds here, graph of I dot append I minus 1, and here itself I can have another dictionary that can store my indices, collections dot default picked list, and then indices of AR of I dot append I. Cool. So this would be something, and then I can start my BFS, like pretty straightforward. Q dot append 0 and 0. So this is my starting index, right? And then I start off the BFS, the weight and the node will be popping them out. And then for, yeah, there comes the catch rate. Okay, not yet. For neighbor in graph of node, my new weight would be, oh no, not required. I think I can just keep a visited array here. Visited is set, sorry, a set if neighbor not in visited dot add neighbor, and then q dot append neighbor, and okay, sorry, it should be weight plus 1 and neighbor, right? Okay, I traverse through the graph this way, but I'll also have to look for the indices, right? So how do I do this? Because I have a visited array here. What if I mm, anyways, yeah, let's just do this and see. For neighbor, again neighbor and indices of ARR of node, q dot append weight plus 1 and neighbor, right? And if n minus 1, then return weight, right? And then I can return minus 1 here. In case if it's not reachable, let me run this once and check. Okay, it's working fine. I'm not really sure about this. Let me submit it. Yep, as expected. Maybe I can go ahead and clear the indices because they are no more required, right? Dot clear. May use this case. Then run it now. All right, so this is solved. I was worried about this, but anyways, it's not really necessary, I guess, or maybe we can try, but I'm not sure if this would be a great idea per se. Visited dot add neighbor. does this? Like, okay, so this is 355 millisecond. Let's see what would this give. Hmm, this is interesting. Yeah, cool. So yeah, that was the problem. Yeah, surprisingly, it's a hard one, but yeah, thanks for watching. If you have any doubts, do let me know in the comments. Thanks. Bye.